And we're going to roll. Okay. Oops, no, that's not the one I want. Apologize. I got two PowerPoints open, and I don't want that one. I don't want types of circuits yet. That's going to be maybe at the end if we've got time. I want that. Potential difference. Click, click. Okay. All right. So current is the flow of electricity through the circuit. You also know of another property called voltage. I've been making circuits for you. I actually should have grabbed some equipment to make one. I will in a moment. And I've always got a power source in there, the battery. And we already know that there's a special property about the battery that is called the volts. And you all know that because you all have used batteries in the past. You know that if you've got to change the batteries in the smoke alarm because it's the time change, that's what they tell you to do. What kind of battery typically goes into a smoke alarm? Anybody know? How many volts go into the battery into a smoke alarm? Does anybody know? Does anybody? The big square ones. Well, the little square ones, but you know, they're square. Does anybody know how many volts they are? Yep. Nice. That's a 9-volt battery. And so you know that it's got something like 9 volts. You don't know what the volts are, but there's 9 volts. And if we have a regular little battery, or we call it a cell, how many volts is a regular little battery? Any ideas? Yep. 1.5 volts. Does anybody know how many volts is in a car battery? Car battery. Anybody know how many volts in a car battery? Typical car batteries and lawnmower batteries and motorcycle batteries, they tend to be 12 volts. They're 12 volts, all right? Okay, so what is this volts? What does the volts mean? And that's what we want to talk about. The technical term for voltage is actually potential difference. I'll explain what that means, but I'll often talk about volts. I won't necessarily use that term potential difference. Now that was the worksheet you were supposed to hand in. I was going to do a quiz, but because you were all out trick-or-treating, I don't know whether you were or you weren't, we're going to have that quiz on Monday, and I'll state that at the end. Okay. I'm going to bring the whole thing up. I'm going to put my circuit up there. And once you're done writing, I will explain to you what I mean, or what volts or potential difference means. Yes. Okay. Put the calculator down. Thank you. You can see that this note is about energy, all right? And energy is one of those terms that we use, or that you use and you've been taught, and that you use in many different ways. You know that the sun is a source of energy, right? You know that plants use that energy. You know that when you plug something in, you get energy, right? It's a source of energy. You know that if you eat a good breakfast, that you have energy, all right? But this is kind of a tricky little term in terms of physics. Energy means simply that something can do work. In other words, that something can do something, give a push on something, or make something move, or perhaps cause electrons to move, all right? So what we're talking about here is electrical energy, all right? Now notice we use the term here, electrical potential energy, all right? Now I got to tell you a little bit about what potential energy is. As electrical charges pass through the source, they gain electrical potential energy. Potential energy is any energy source that can be stored in an object, all right? In a battery, the chemicals have this electrical potential energy. It means it has the potential to do something. I can put potential energy into this cart simply by picking it up, all right? I've now given that cart potential energy, but it doesn't have electrical potential energy, it has gravitational potential energy. Because if I let it go, what's this cart going to do? This has got to be the easiest question that I've given Chloe. If I let this cart go, what's it going to do? It's going to fall to the earth. Why? Because there's a force pulling it to the earth, the force of gravity. And so because I separated it from the earth, I've given it potential energy, all right? And potential energy can be dangerous, all right? Potential energy has the ability to do things that might not be very nice. You feeling nervous? Yeah, because there's some potential energy nearby. You don't want that hanging around, so I'm going to take it away from you so you're not so nervous. So this is gravitational potential energy. What did I do with my other prop? Here I've got an elastic band. What's the matter? You're feeling nervous again, aren't you? That's because there's potential energy in this. I had to pull on this in order to store some energy in it, just like I had to pick up the cart to store some energy in that. This is called elastic potential energy, all right? Things like bungee cords and things like springs have elastic potential energy in it, okay? And I can get that energy out by letting go, sending it across the room. That would be irresponsible. I'm not going to do that, okay? So that's another form of potential energy. When an electron, which is in the battery, maybe let's say it's in this spot, and due to the chemical reactions, that electron ends up right there, just outside of the battery, just outside of it. What's that electron going to want to do in that position? Yeah? It's going to want to get to the positive side. In other words, the battery acted almost like me picking up the cart and getting it away from where it wants to be. And now that it's outside of the battery, it's going to fall, not to the earth, but it's going to fall back to the plus, through the wire, through the load, and give that energy up. Okay? If I were to drop this cart and have it land on my toe, I would scream and yell, because that cart then would have dumped its energy onto my toe. Would have been pain, well, my right toe, my left toe. Anyway, you guys get the idea. The left toe would just be inconvenient. It would show I'm tough. Anyway. So that energy then gets deposited into my real foot, and it causes me some pain. In this case, the electron falls through the load. It might be a motor, and it causes the motor to spin as it falls through it. Okay? So, when electrons go through a load, it gains energy, like somebody picking it up. We call this a voltage gain. Please write that down. So through a source, we have a voltage gain. And if I took my voltmeter, just like you guys did with your little cells, and I touched it across the battery, I'm hoping someone out there is reading it. Can somebody stand up and read that? Yeah, you got to stand up. 1.21, it's about 1.2. Through this battery, it has gained 1.2 volts of energy. Okay? It travels along the wire. Because the wire is a really good conductor, it doesn't lose any of its energy in the wire. It actually loses a tiny little bit, but we're not going to worry about it. Then it goes through the load, and it drops the energy off. All right? It drops that energy off. And so at the load, we call it a voltage, what do we want to call it? A voltage loss or a voltage drop. I've used both terms. I've called it a voltage loss or a voltage drop. We'll call it a voltage drop. It doesn't matter. And you can imagine it as if it's falling towards, like due to gravity. It is falling. It's falling due to an attraction of the opposite charge. All right. Now, the voltage is measuring how much energy the charges carry. So the energy the electrons have is not due to it carrying it on its back, but I find that sometimes a good way of thinking about it. The energy comes from the fact that it wants to be attracted to the other side. But I like to think of the charges, I like to think of the coulombs as little dump trucks. And in the battery, the trucks get loaded with energy. And then they go through the circuit, where the circuit's like the roads, out to where they've got to use the gravel. Let's say they're fixing something. And at the load, they drop off the gravel. They empty their energy out. And then the electrons head back to the source to reload with energy. That's the way I like to imagine it. It actually makes some of the calculations we're going to do later on a little better. So, at a power source, the charges, the coulombs, fill with energy, and at the load, they drop their energy off, a voltage drop. Let's do some calculations. All right. Oh, first let's talk a little bit about putting cells together. I do have to talk about that first. What happens if I link more than one cell together? I just typed this up the other day, so I might have screwed this up. When more than one cell is connected together, correct. That is me typing quickly and missing it out. When more than one cell is connected together. So there are two ways in which I can connect batteries. I can connect them in a row, positive to negative. Put two of them back to back. And this is the circuit symbol for two cells put together in a battery. Or I could connect them side by side. A negative connected to a negative and a positive connected to a positive with some kind of wire. And I just want to talk about what happens when those charges go through there and how they get loaded with energy. Now, I've already told you the answer. When we connect them positive to negative, the volts add up. And if we think of it like dump trucks, it kind of makes sense. If each of these cells is 1.5 volts, and the dump truck comes along and gets 1.5 volts of energy in the first cell, and then goes through the second cell and gets 1.5 volts of energy, how many volts of energy will have that particular dump truck been loaded with? I'm going to ask it again. If these two cells are connected in a row, and the first one fills the dump truck with 1.5 volts of energy, and the second cell fills the dump truck with another 1.5 volts of energy, how many volts of energy will have that truck picked up? Travis? 3 volts. Good active listening. So when we run them in a row, the volts add. Okay? When we put them side by side, yes, a truck's going to get loaded with 1.5 volts. It's now ready to head out to the job. All right? Now let's imagine, what if this truck got lost and somehow pushed its way backwards through the battery? Even though it wouldn't do that, because it would be repelled away from the negative. But let's imagine that it pushed its way backwards through the battery. What might you imagine happened to the 1.5 volts that were on that dump truck if it were to go backwards through a battery against the work? Yep. It would drop it back off. So if that dump truck picked up 1.5, headed down here and went backwards through this battery, how much would it have left at this point right here? If it picked up 1.5 and then for some reason got lost and went backwards through the battery, yep. Nope. Picked up 1.5 and then went backwards, yep. 0, because it's dumped it back off. So when you have them sideways, it doesn't matter which battery they go through, they pick up 1.5 and then they head off and dump it off. They don't go backwards through the battery because they would drop their volts back off. Wouldn't be a gain. So in the end, when you have the batteries connected side by side, it just means it lasts twice as long because you've got twice as many batteries to load up with 1.5. But it doesn't make it any higher. It doesn't make it 3. Okay? All right. So that's what happens when we connect batteries together. And the next part is going to be my equation. And if you're still writing, I'll put the equation on the board. So the equation for volts is V equals E divided by Q. All right, and I'm going to write this on the smartboard in a moment for those who are away, but I just want to give you a head start. You'll notice that this equation looks a lot like this one in that we've got one variable and then a fraction, right? Which means we should be able to rearrange it very similarly. I would really like to do the rest of this on the smartboard if I could. We've already seen Q. Q is the same Q that we had yesterday. But it's on the bottom. You're right. All right. So, V is the potential difference or the voltage. Again, Potential simply means the potential energy difference coming from that potential energy. And it's called voltage or potential difference, and it's measured in, well, this one's pretty easy. What do we measure voltage in? Yep, volts. V. Okay? Q. Q is the charge. That's a good question. I don't know the historical beginnings of using Q for the charge. I don't know what it is. Somebody at some point when they first created that first equation, they decided to use Q. We've been using it for years. So what do we measure Q in? Coulombs. What letter? C.
Is there another equation in energy?
No, these are the only two that we're going to deal with that have C's. This, what do you think the E stands for? Yep, that's the energy that the coulombs or the charges are carrying around. Again, I imagine the coulombs as being the trucks. Coulombs carrying energy. Energy. Energy is measured in, anybody know? Yeah? It's a capital J. It's a joule, named after James Prescott Joule, very important physicist. Did lots of work explaining how there were different forms of energy, how there's electrical and chemical and gravitational. He was able to figure out how they're really all the same thing. Smart guy. All right. Well, before we get going, let's rearrange this equation like we've been doing before. If I wanted just energy by itself, and I want to move that Q to the other side, the Q is now a division. When it goes to the other side, it's going to become the opposite, mathematical thing. So what is E going to be equal to? What is E going to be equal to? Rachel, what do you think? Well, because I need to pick on a little bit on people who are sometimes not wanting to do this stuff. And you're one of them. This was a division over here on this side. I've got to bring it to this side so that I can get the E by itself. When we move that to the other side, remember it does the opposite calculation. So what's it going to become on this side? And so what's my equation going to be? So what is it going to be? E is going to be equal to what combination of V and Q? VQ. V times Q. Excellent. Okay? All right? What's my last possible combination? What else can I get by itself? Yep. Q. Q equals, now I got to bring the V to the other side. Go ahead. What do you got? Ooh, no, it's not V over E. Yep. It's E over V. This V is going to become a division on the other side. E over V. Okay? E over V. All right. Now we know what the symbols are. We know the different permutations. Now we just have to do some examples and pick out which equation we want to use. All right. You know the drill. We got to write it down. It's just the way it goes. They're not exciting, I know. Yep. Oh. How about we just use this one right now? What's that? No, let's just use this one for now. There's one here. There's one here. Let's write it down, folks. That's it? That's all you're going to write? Minimalist. You're a minimalist. How are you going to know what the question is when you go back to study?
Look at your video.
You're making a note? You're making note of to go back to the video to look at the question?
Yeah.
All right.
So
Okay, that's a thing. Again, the way I like to attack these, you know what? Sometimes I really don't like reading all the words because I'm not a word reader. But what I do is I pick out the numbers and the units. And that tells me what I got to put where. Again, I'm too lazy for you guys. Again, I'm lazy on checking the homework. I'm lazy on some other things. And I've already told you that if you didn't write some of the numbers down before, that it wouldn't be a big deal. And you guys are all taking advantage of me. I'm going to write it down. 350 capital J. What is that in my equations? All the regulars can put their hands down. All the regulars can put their hands down. Joules. What is it? Chloe. E. Nice job. Blah, 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 blah. 2.0 C. What is that? Yep, Jay. Q. And therefore, what must I be looking for? Danton. Sorry, say that again? So you're telling me T is equal to E divided by Q? Oh my goodness, you're right. I'm getting it all mixed up with the last equation. V equals E divided by Q. Thank you. I was thinking over there. I'm glad you complained. That's a good thing. E, 350 joules. Q, 2.0 coulombs. How many volts is that? Yep. 175 volts. And if you're really going to be lazy without a therefore statement, if you want to be really lazy, put that in a box for me to see. All right?
Is that a therefore statement?
Yeah, sure, therefore, but put it in a box. Because when I'm marking things, I look for that final answer and then I work my way backwards to make sure you did it right. So I like to spot where the final answer is. That other sheet you're going to be turning in, I've got another sheet that you're going to be handing in. Okay, can I continue?
Yes.
A 1.5 volt cell can deliver 4,580 coulombs of charge before it's dead. So we're saying that you put a brand new cell in there, you let it run a motor or a light or something, and you keep on going until it stops. How much energy was delivered by that device?
Oh, no, never mind.
All that you've said is correct. You're right. If you're multiplying by a decimal smaller than 1, it should make the number smaller. Yes. Yeah. But it is 1.5. Correct. Again, you should hopefully be going ahead of me. Marshall, are you done this question? You have an answer? Nice. Let me catch up to you. 1.5 V is V. It's kind of obvious. 4,580 coulombs is Q. Therefore, we're looking for E. E is equal to be honest, I don't have that memorized. I always got to go back to my V equals, whoops, look at I screwed it up. V equals E over Q. Oh, and I'm going to bring it to the other side. What's the equation I'm looking for? I want to know the equation. Robert, what's the equation? VQ, which means I'm doing 1.5 volts times 4,580 coulombs. And Marshall, what'd you get for a number? 70. And what's the unit? What letter am I putting behind it? J, joules. And then I put a nice box around it. Parker, make sure you get that number on your calculator. Make sure you run it through the calculator. Did you get that number, Chloe, on the calculator? Run it through a calculator. Rachel. You need to be more specific. Okay. All right. Nope, this is important. This is important. This is the way we did this. For those of you who have a device going, if you could copy the next question down, that'd be great. This is important. Now, pay attention. I wrote down this number right here, right? And I recognized this unit right there, okay? And then I looked back to my note. Flip back in your note and look at the equation. Where's the note that you just took moments ago?
Oh, this,
Yeah. So what of our symbols in our equation here is represented by V? Which of these things in this equation is represented by the unit V? The voltage. So I know this number right now. Okay. Then I write down 4580C. And I ask myself, which of these things is represented by C, coulombs? The Q. So now I've figured I've got the V and I've got the Q, so I need to solve for E. Okay? And therefore, I'm going to rearrange this equation to move this Q to the other side, just like we did when we wrote down those three in our note. Which equation is that? If I want E, what is the equation for E by itself? Waiting on you, Rachel. V times Q. That tells me I'm going to multiply these two numbers together. Then I put them in my calculator and I'm done. But those are the steps. Use the units to identify which of the letters in the equation we're dealing with, figure out which one we're trying to find, get the right equation, and then do it. That's how we do it. Okay? Does that make sense? That's what I'm looking at when I'm doing these questions. Now, number 3 is fun. Number 3 is a fun one. A typical lightning bolt. Look at what I did there.
Hallie's already making fun of you.
Who's making fun of me?
No, I think I know why you spell all these words awfully. Because you spell all those big words like coulomb, correct? So it's just like messing up your words.
Bolt. A typical lightning bolt. But it could be bold. Like lightning is bold, isn't it? Anyway. A typical lightning bolt can produce, keep writing, can produce 200,000 amps of current for a time of 2 times 10 to the negative 6 seconds. You're right, there is no amps in this one. What is the charge that passes through the tree to the ground? Now, what numbers do I have? Let's start writing it down. 20000 amps is what? What letter is amps? What letter is amps? Yep. It's I. It's I. In 2 times 10 to the minus 6 seconds. What is that? What is that in our symbols? That's a T. What can I get if I have I and T? Yep. I can get Q. We don't forget the equations we learned before. They're still true. So we can now use our Q equation to get Q from the other one. So, Q, what's it equal to? What's it equal to? I times T. So we're first going to do an I times T calculation. 2,0,0,0,0 amps times 2 times 10 to the negative 6, negative 6 seconds. Did I teach you how to use that button yesterday? The E or EXP button? I'll walk you through it. Have you got your calculator nearby? Let's get ready to roll. Again, we're participating here. 2. That's the 2 button. It's always funny. 2,0,0,0,0 times, looks like an X. Are we okay? Did we push it? 1, 2, 3, 4, 5. Come on, folks. Yes, you're looking for your EE button or your EXP button. All right? Which means, here's how it goes in next. 2, then you're looking for your EE or EXP button. Press it. Then negative 6. And then you can equals away. Because it's the number in the question. Oh, you press there should be a plus minus button. For a negative, you're looking for a button that looks like this. Plus minus. Some have minus in brackets. Some have what you mean like this? Yeah. Oh, that's interesting. Yeah. You'll have a plus minus button. Huh. I would have never thought that the positive negative button was going to bring this lesson completely off the rails.
Can you help me find it?
I didn't think that that was going to be the one to stop us. Yes. What's that? Negative 6.
Equals 0.4. That's the right number.
Yep, that's the answer. This is a big number times a small number. What do we get? Yep, what do you got? I think it's 0.4. Is it 0.4? You must have had an extra 0 here on your 200. 0.4. Did you get 0.4? Nice. In a moment, I'll help you out find it. Let's keep going. What's the unit? What did we just find? Coulombs. Coulombs. Now we've got Q. Now we can move on to the next question. Yeah, there's B right there. If the voltage of the lightning strike is 1 times 10 to the 9 volts, how much energy was delivered to the air in the tree as it busted through the air in the tree? You have the volts. 1 times 10 to the 9V equals V.
What about the other two?
Well, what did we learn from the previous question? What do we now know?
We already know the other two. No, we know 0.4 is coulomb.
Ah, which is what symbol?
Q.
Q. So we know Q and we know V.
But doesn't that...
We want to get E. No, we don't want T. How much energy? We want E. Well, V is equal to E over Q. I got to bring this Q to the other side. What happens to the Q? What is the equation when I bring it to the other side? E equals, I'm multiplying V times Q. Yep, it's a big number. There's a lot of volts in a lightning bolt. Yep, but you can use your EE or EXP button. 1 times 10 to the 9, I would, times 0.4 coulomb. Oops, look at what I did. I put the coulombs on the outside of the brackets. 0.4 coulombs equals.
Wow.
Do you have an answer, Rachel? Yeah, I say it. This is going to build your confidence. What do you got? What's that? Oh, it didn't build your confidence. Oh, I'm sorry. What do we have? What do we got? What do you got? 400 million. Tell me zeros. Tell me zeros.
I got 8 zeros.
1, 2, 3, 4, 5, 6, 7, 8. Is it 8 zeros?
It is 8 zeros, yeah.
So if I put a little comma there, thousands, millions, 400 million. 400 million. What's that? There's 6 zeros in a million, so there's 400 millions. What's the unit? Joules. That's a lot of energy. You don't want to be in that circuit. That doesn't end well for you. No, because that's a good question. On the ball thing, the voltage is high, but the current is incredibly tiny. And that's why when we do the circle thing, right, that circle thing, that the voltage was high, but the current is incredibly tiny. So I only send a very tiny few joules through you when I torture you. Okay, all stop. All stop. You now have a worksheet also to work on. It's on Google Classroom. I'm going to want it handed in, which means you're going to have to hand in 2 sheets on Monday. We're also going to have a quiz on Monday that's on the symbols and on these calculations. So right now, you're going to work quietly. If you are of the group that still thinks that they have no idea what's going on, you're going to come up to me and I'm going to help you out. All right? Yep. Quickly. Hold on 1 second. This is coming to an end here. I got to stop my recording.